A quartic graph is one which has equation y is equal to a x to the power 4 plus b x to the power 3 plus c x to the power 2 plus d x plus e, where all these numbers a, b, c, d and e are real numbers, and we also insist that a is not 0. So we really do have a power 4 curve. We need to understand how to sketch curves of this form. Let's start by trying to understand the simplest possible case, y is x to the 4. We can do this by plotting some points. Let's just go for the integer values of x, and we'll do values of x from 0 up to 6, both positive and negative. By raising those x values to the power of 4, we get the following points. It should be obvious that the y-axis is a line of symmetry, because if we have the same x value whether positive or negative, we will get the same y value when we raise it to the power of 4. The curve which goes through these points looks like this, and this therefore is the graph of y equals x to the 4. It's a little similar to a parabola, a y equals x squared graph, a little flatter at the bottom, although it should be noted that it only touches the x-axis when x equals 0 and at no other points. If we are trying to draw the general quartic graph, ax to the 4 plus bx cubed plus cx squared plus dx plus e, then the values of a, b, c, d and e can change the shape of this graph quite considerably. We're starting with the y equals x to the 4 graph we've just drawn, but if we allow the values of those constants to vary, we can get an extensive range of different shapes. Our challenge will be to know how to sketch these curves, whatever the values of a, b, c, d and e we are given. We'll begin with this example. Sketch the curve with equation y is x plus 3, x plus 1, x minus 2, x minus 4. This is given to us in a nice factorized form which will make things easier for us. Let's begin by finding the intersection with the y-axis. When x is 0, that means that y is 3 times 1 times negative 2 times negative 4, which is 24, so therefore we know this curve passes through the point 0, 24. When y is 0, so we're finding the intersects with the x-axis, that means that x plus 3 times x plus 1 times x minus 2 times x minus 4 is 0, which means that either x is negative 3 or negative 1 or 2 or 4. So we have the following intersection points with the x-axis: negative 3, 0, negative 1, 0, 2, 0 and 4, 0. We can also investigate the behaviour of this curve as the value of x gets closer and closer to infinity. Now if x is very large and positive, then each of these 4 brackets will be a large positive number, which we're then multiplying together, which will give us a very large positive answer as well. So as x tends to infinity, y tends to infinity. What happens as x tends to negative infinity? In other words, if x gets smaller and smaller, larger in magnitude, but getting increasingly negative, then every one of these 4 brackets will be a very large negative number. But when we multiply the first 2 negative numbers together, we will get a positive number. When we multiply the last 2 negative numbers, we will get a positive number, and then multiplying those 2 positive numbers together, we will get another positive number. So y will tend to infinity in this case as well. Intuitively, this means that as we go either in this direction or this direction, then the y value gets bigger and bigger. So the curve will come in from a very high up value, maybe come down and do some stuff, and then end up again in a very high value. Let's plot this information. Firstly, we have our intersection points. The curve which goes through all of these points looks like this. Now, apart from a few details, such as the fact that we don't really know quite how far down the minimum points of the curve are, or how high up the maximum point is, or whether the intersection with the y-axis is to the left or the right of the maximum point, this must be the general shape of this curve. We know the curve starts off in this top left. It must therefore cut through the x-axis at our first intersection point and go down. It must then turn around to go through the second intersection point, and then through the y-axis at a positive value. Similarly, it must turn around so that it cuts through the x-axis again, turn back around so it cuts through a fourth time, and then head up to the top right. In our next example, one of our brackets is a quadratic factor. It's always a good idea to try and see if we can factorize any pieces like this. So, if we start off with y is x squared subtract x subtract 6 times 2 subtract x times x subtract 3, then actually it is not too difficult to factorize that first bracket. Let's see if we can do it on site. We must have an x and an x at the beginning. We need two numbers which multiply to -6 and add to -1. That will be x subtract 3, x plus 2. We still have this 2 minus x. We still have this x minus 3. And x minus 3 was also one of the brackets that we have just got in our factorization. So we can write this more concisely as y equals x plus 2, 2 subtract x, x subtract 3 squared. Now we can begin our usual method. If we have an x of 0, that means we will have a y of 2 times -3 squared, which is 36. So therefore the curve passes through 0, 36. If we have a y of 0, that means that x plus 2, 2 subtract x, x subtract 3 squared is 0, from which it follows that either x is -3, or x is 2, or x is 3, so we have intersection points -3, 0, 2, 0, and 3, 0. But this last point is in a bracket which is squared, so this last one is a repeated root. As x tends to infinity, what happens to y? Well, let's look at our factorized form. This first bracket will be a large positive number. This second bracket will be a large negative number because we're subtracting the large positive x from 2. It doesn't really matter what happens inside this bracket because we're squaring it, so this bit will be positive. So the whole thing, positive times positive, is going to be a large negative number. The y is going to tend to negative infinity. As x tends to negative infinity, what about y on this occasion? The first bracket will be a large negative number, the second one will be a large positive number, and once again this last piece is being squared, so that will be positive. Positive times negative, that's also going to be a very large negative number. So we will have a graph which starts off down at the bottom left and finishes down at the bottom right. We have our intersection points, and because of our understanding of where the curve starts and finishes, it must have this shape. Let's look at one of the very interesting features of this. Our intersection point at -2, 0 is where the curve just cuts through the axis. Our intersection point at 2, 0 again has the curve cutting through the axis. But our intersection point at 3, 0 is where the curve just touches the axis. This is because x equals 3 was a repeated root. In this example, we have to sketch the curve with equation y equals x plus 2 squared, 3 minus x squared. So, if x is 0, then y will be 2 squared times 3 squared, which is 36, so we have an intersection point at 0, 36. If y is 0, then we have that x plus 2 squared times 3 subtract x squared is 0. So therefore either x is negative 2 or x is 3. So we have intersection points with the x-axis at negative 2, 0 and 3, 0. But in both cases they are both repeated roots, because they are both in brackets in the factorization which occur twice. What about the behavior as x tends to infinity? Well, in this case, whatever happens inside either of these brackets, they will both be squared, so both will be positive numbers, which we will then multiply together to get another positive number, so y will also tend to infinity. And it may have occurred to you by this point that because of the x to the 4, because of the even power in these equations, the same thing will happen whether we go to positive or negative infinity in any case. So once again, we will have a curve which begins up here and finishes up here. Plotting our intersection points, we can see that the only way to fit a power 4 curve through these points is like this. Note that this time, as both of our intersections with the x-axis are repeated roots, repeated twice, the curve touches at both of those points. It doesn't actually cut through the x-axis. In this example, our factorized form for this equation has one bracket to the power 3 and one linear bracket. Putting x equal to 0, we see that y would be 2 cubed times 3, which is 24, so we have an intersection point with the y-axis of 0, 24. If we were to put y equals 0, we can see that x plus 2 cubed, 3 minus x, is 0, so therefore either x is negative 2 or x is 3, and we have intersection points at negative 2, 0 and 3, 0. But the first of these points is repeated 3 times. We could say it is a 3 times repeated root. We can see that as x gets increasingly large, then this bracket will be a large positive number to the power of 3, large and positive. This bracket will be a large negative number. Multiplied together, we get a large negative number. So y tends to negative infinity. And we have already discussed the fact that the behavior will be the same as x approaches both positive and negative infinity. It may be clear by this point that the only thing we have to do to work out what is the behavior of the curve as x tends to plus or minus infinity is to look at the coefficient of x to the 4. If we expanded all of this out, we would get a curve that began y is negative x to the 4 and then some more pieces. It's the coefficient of x to the 4 that matters. If we have y is a x to the 4 plus all the other pieces, then if a is greater than 0, we will have a curve which starts off and finishes up above the x-axis. If we have an a which is less than 0, we'll have a situation where the curve begins and ends below the x-axis. So we can plot our intersection points, and because of our knowledge of the shape of this curve, it must have this appearance. Now again, there are some things we can't be entirely sure of with this curve, such as whether the maximum point is to the left or the right of the y-axis, but the important thing to note here is that at our intersection point with the x-axis, which only appeared once, the 3, 0, the curve cuts through at that point. With our triple repeated root, we have one of these situations where the curve cuts through the x-axis tangentially. It levels off to have a gradient of 0 as it cuts through that axis. Another example with a repeated root, this time a root repeated 4 times. It should be clear that we have an intersection with the y-axis of 0, 16, and an intersection with the x-axis of -2, 0. But this x-axis intersection is a 4 times repeated root. Also, because we have a positive coefficient of x to the 4, we will be in a situation where our graph begins and ends above the x-axis. So plotting our intersection points, we will have a curve which looks like this. How can we be so confident that that is the curve we are going to get? Well, if we began with the y equals x to the 4 curve, which was the first example we looked at, how could we get from that the curve y is x plus 2 to the 4? X has been replaced by x plus 2, which is the same thing as x subtract -2. So therefore our transformation work tells us that what we have is a translation of the original curve by -2, 0. So starting with our y equals x to the 4 curve, if we do a translation of 2 units to the left, we end up with the curve we require. This curve is given to us in the form of 2 quadratic factors. It's easy enough to see that the intersection with the y-axis will be 0, 7. What about the intersections with the x-axis? If y is 0, then either one or the other one of these quadratics must come to 0. But it's very clear to see that the first one can't possibly come to 0. If x squared plus 1 was 0, that would mean that x squared is -1, and that clearly has no solutions. What about the other quadratic? Well, the easiest way to check if that's got any solutions is to look at its discriminant, and its discriminant is -5 squared subtract 4 times 1 times 7, which is 25, subtract 28, which is -3, and being less than 0, we can see that the second quadratic also has no solutions. So there are no intercepts with the x-axis. If we expanded it, we would have a positive coefficient of x to the 4, so we do know that it begins and ends above the x-axis, and what we have just done shows us that it will never touch the x-axis either, so it lives entirely above here. But apart from our intersection point, there's nothing else we can really conclude about this curve. It turns out that this curve has the following shape. But with our knowledge at present, there would be no way for us to know that. You need to be aware that there will be cases where we do not have enough information to sketch this curve. Later in the course, we'll develop methods of finding the coordinates of the minimum and maximum points, and if we knew them, then we certainly would be able to have a good go at sketching this curve. But based on the information we have just from axis intercepts and the general shape of the curve, sometimes there's not a lot that we'll be able to do. Let's conclude by looking at our general method for sketching quartic graphs. First, we find the point of intersection of the quartic with the y-axis. Then we find the point or points of intersection of the quartic with the x-axis, if there are any. We then have to identify the nature of the intersections with the x-axis. If we have a root which only appears once in our factorization, then the curve cuts through at that point. That was the case with all of the roots in this example. If we have a double root, one which appears exactly twice in a factorization, then the curve will touch the x-axis at that point. That was the case with the x equals 3 intersection in this example. If we have a root which appears exactly 3 times, then the curve will cut the axis tangentially at that point. That was the case with the x equals -2 intersection in this example. And if we have a root repeated 4 times in a factorization, then the curve will touch the x-axis at that point. That was a situation in this example. And finally, we have to determine the general shape of the curve from its behavior as x tends to infinity and negative infinity, but we know that we do this by inspecting the coefficient of x to the 4. If we have such a coefficient which is positive, we will have a curve which begins and ends above the x-axis. If we have a coefficient of x to the 4 which is negative, then we will have a curve which begins and ends below the x-axis.